And talking to Tom Richards, he is on a lecture tour. Instead of a book tour, a lecture tour sponsored by the Deep Foundations Institute, or DFI. And he has this lecture in person for us today. And he also has another lecture, and we're going to be sponsoring that through CalGeo as a virtual lecture. So be on the lookout for that. So enjoy his presentation this morning. There'll be another one coming up that he's going to do. Tom says he's a retired engineer, but he doesn't seem very retired. He is now a consultant with Nicholson Construction Company, and for over 30 years he was with Nicholson, dealing with technical aspects of a multitude of specialized geotechnical projects using micropiles, anchors, soil nails, diaphragm walls, and numerous grouting techniques. Tom's responsibilities included design, quality control, research, testing, and instrumentation. He's still active, on numerous committees of DFI, ADSC, PTI, and ASCE, leading to frequent commenting on FHWA and other industry documents. He remains active on a few DFI and ADSC committees. He is also a member of the MOLS. In 2019, Tom was awarded the Distinguished Service Award from Deep Foundations Institute. Tom also informed me that he is active now in philanthropic capacity in a trust set up by DFI as well. Correct, Tom? Please give a round welcome of applause to Tom.
Well, we're going to start with a word from our sponsor, DFI. And the first thing I'd like to know is who's a member of DFI? Decent representation. That's probably what brought you here for this particular topic. So I won't delve in this too much, but DFI is a very diverse group. It has all these people who are involved in the Deep Foundations profession. And here's a pie chart of the demographics. You can see a decent balance of contractors and engineers. There's a huge part, that blue part that says academics, and truth is that's really includes the students as well, and the academics are only like 4%. And the students are really high because every student who's ever applied for a scholarship becomes a student member for free. And suppliers are an important part of it. They help tell us about the material aspects of the different technologies. DFI has 28 technical committees. There's one on seismic and lateral loads that Ben's probably pretty active in, and there was something else mentioned yesterday. We fund some research that was mentioned yesterday in Ben's talk as well. And the 28 technical committees cover all the technologies, all the foundation type technologies that you see back there with the affiliates. There's lots of good publications from DFI. Every year there's an annual conference. Most of the committees have a manual about that technology that's kind of like best practices. There's a high quality magazine published 6 times a year. All this comes with your membership. You have to go to the conference to get the proceedings. They're available free later. And the last thing is a DFI journal. So that's a peer-reviewed papers, and that's published about twice a year. And it's a whole lot easier to get into that and faster to get into that than the ASCE Geotech Journal. But there's more. When you become a member, you get access to one mine that has over 140,000 documents. Many of them are about mining, but it includes all the old DFI documents and some Department of Interior and Safety Organization documents as well. And the last thing, I'm a member of the trust, so we raise money to donate, to encourage students to go into the geotechnical and especially the deep foundations profession. And so far, there's $5 million of assets, $1.6 million given out to 450 students, over 450 students actually, at 74 colleges and universities around the US and Canada. And here's a list of the sponsored trusts. And one that I'd like to point out for the locals is Michael Condon. So there's a Michael Condon Scholarship Fund that Condon Johnson was active in raising money for. And there's a Terracon one down there too. Okay, now we're going to get into work platforms. And I hope by the time I'm done, I convince you this is an important topic for us to be involved with. And it's really about lessons learned I've had in working with the tools of that, engineering tools that are out there for that topic. So we're going to talk about why it's a topic, the resources available, and then dig into some of the calculations. I'm going to show some videos and photos that I've collected from lots of different sources, lots of different contractors, lots of different equipment suppliers. I encourage you to not care about any of that. Don't care about the contractor or the equipment supplier. I want you to look at what's the rig doing. Is it walking? Is it drilling? Is it pulling tools out of the hole? And I want you to look at the position of the way the rig fell relative to where the operator is. So our first thing is a YouTube video that was produced by Keller and Solitanch and Menard. And this was produced back when they were fierce competitors in Europe. Now Menard and Solitanch are related, but it shows you how important they think this topic is to cooperate and produce this video. Hope you caught that operator's face. That was the big hit before, now it's like a flashback to a normal day on the site. So this is about where we want to head. High quality platforms, marked so that people don't drive off the edge. explosives are certainly a more European thing. Mark the perimeter so they know where they can drive. Certainly walking on inclined surfaces are a big problem. We'll see some of the charts from the manufacturers tell us what So the images at the beginning were all a reenactment, and it says that they didn't happen, but I think if they dug deep enough, there's probably some parts of that story that really are true. And just because that one was a reenactment, here's one. Here's one that's real and recent. It's at night. It's always harder to control safety at night and see where what things are going on. Oh my, here we go. That's a bad day for everybody on the job. Oh, shoot. Here's another one. Now this video is a little quirky because it's a video of a computer screen. That last rig was walking, this one's walking. When most of us saw the pictures on the right and other videos that are available on YouTube, we said, we don't think this is a work platform thing. But when you see the image on the left, you can tell he was really sinking in. So I hope those videos affect your stomach like they do mine. So here's a bunch of still pictures, and this will be a little slower pace, so maybe you can see what activity is going on, drilling, extracting, walking, and also see where the rig operator is. That's the same one as the last one. On most of these rigs, the operator, so this actually went to the operator's side. The operator's on the left-hand side when you look from the back. Those two pictures were the same. This one, there's a chance that he was pulling tools. Can't really tell for sure. Some tools are out and got bent on the temporary shoring. Here's a whole collection. Another one on the front right track. Going forward, front right track. In this case, it's hard to tell what happened, and this was a crane system as well. There's one towards the operator. Another one likely towards the operator. Another one that's actually likely towards the operator. You can see that there's impacts, blocking traffic. This is going to make a bad day for a lot of people on this project. In Toronto, a guy died. In this case, his operator cab was right there. This one's interesting. It's one of the few that I've found that the rig went over backwards. And I know the contractor on this job, and off the record, with a source that I believe is pretty reliable, this rig drove into a hole behind it. This one actually happened when rain fell overnight and saturated the surface. So, I might have led you to some observations there. Think about your observations, and then here's what mine are. It's often over the corner of the tracks, and we'll see why that is when we look at the calculations. It's often opposite where the driller's sitting. I noticed more this time that we're towards the driller, but very often it's opposite the driller. And not a single one of them appeared to be while drilling the hole. And you'll see that becomes an important observation when we do the calculations. So here's what we should have. We should have geogrid, also a separation geotextile would be good, and some gravel to make a work platform. That is the calculations I'm going to talk about today. There are also guidance documents from Europe about how to do that with a cemented, prepared surface. It's hard to think about combining them because of strain compatibility. And you can use crane mats. Crane mats work wonders. This is not the most efficient way to use a crane mat, to walk along it, but it's often what's done. So here's the resources available. This is from the DFI working group website. So it's a working group of ADSC, DFI, and PDCA. ADSC is the Association of Drilled Shaft Contractors, but now likes to go by the International Association of Foundation Drilling. PDCA is Pow Driving Contractors Association. ASCE's been involved a little bit, but so under the guidance documents, there's two that I will show covers on and talk about. This one is the US document that says, here's what we should be doing, and gives some guidance on when you should actually do some calculations. And then this one is an ongoing effort with EFFC, which is a European Foundation Contractors Association, to continue this process and make things better. So here's the cover sheet for the EFFC one. You can see it covers a lot of stuff. Working platform design is just one of them. It defines responsibilities, at least how the Europeans see it, and it has a lot of great references in it. Another good document that you can get at from the DFI website is this video. It's a webinar by the guy who was involved with developing the Federation of Piling Specialists spreadsheet, the one I'm going to talk about. And it covers a lot of the nitty-gritty type stuff and nerdy stuff, and he does a really good job. So I'm not going to repeat some of what he does. So the Federation of Piling Specialists is a UK organization, and they got tired of this stuff, and they basically said, we're going to demand this. All of our members are going to demand that we do calculations and prepare subgrades and certify them, and so that's how their practice is. So they developed this spreadsheet to calculate the pressure under the tracks. So we're going to move into some nerdy stuff with this calculation. The first topic we need to talk about is equivalent rectangle. bearing stress, and then we'll look at pulling some data from manuals and stuff you can get from the suppliers. So this is a page from the guidance document, and it shows here's our real pressure underneath the tracks. But for bearing capacity calculations, we're going to convert that to an equivalent rectangle. And they're not alone in doing this. This is an FHWA document about retaining walls, and you can see that the current methods employed by the FHWA, you take that triangular or trapezoidal diagram and convert it to an equivalent rectangle. Really, I think it's pretty standard in even the soil mechanics textbooks. And honestly, there's forces here. You got to look at different weights with different eccentricities. And that's the same type of thing you got to look at with a crane or a drill rig. So what happens is you have this length, you have an eccentricity to the total forces, and you have a length beyond it, and then you say this length on this side is the same as that length over there to get an equivalent rectangle. When you have a triangular distribution of any shape, the whole length of the track or even a partial length of the track, this pressure is 75% of that pressure. Okay, let's see what we can get. I just put this slide in yesterday after I was going to have multiple PDFs and things going, and after Mike's struggles, I thought I better put this all in the presentation. I misspelled sales. This is a sales brochure for the Bauer BG39. I'm going to talk about a Bauer BG39. The other manufacturers give you similar information. We just own more Bauers than the others, so that's what I worked with. So from the catalog, you can get a nice diagram of the rig. This is the basic version. And way up here, we'll blow those up. And you can see it's a pretty darn tall rig. There's 10 meters there, 3 meters, 9 meters. You know, it's getting up there in the air. So we blow up the data, and we can see that it weighs 133 tons. Those are metric tons. Most of the rigs we're using are European made, so we got to work with SI units. And then it turns out that the rig I'm going to work at is called an upgraded version, which really means it has more counterweights and a wider track, a different track setup. They're wider and longer. So if you take that 133 tons from the base machine and add 6 counterweights at 4.9 metric tons, and divide it by 2 tracks at 1 meter each with a contact length of 5.31 meters, you get an answer that's 3 KSF. That doesn't sound so bad, 3 KSF. That's maybe what we would have recommended for the footings on this job, and that was really governed by settlement. So how can this be a problem? How can these rigs be falling over from working platform? By the way, this calculation here with the metric input and the US output was done in a program called MathCAD, which I find to be the most powerful programming language in the world. I am not a consultant to them. So the reason that there's other things going on is there's other forces. There are forces on the main line. So on these rigs, the winch back here comes up over here, and that's the main line, connects usually to the Kelly bar of the rig. In this case, it connects, I'm not sure what it's connected to when you're doing CFA piles. There's an auxiliary line, and I couldn't find a good image of that. That winch comes from here, goes up, over, and to the side. So you can use this like to pick up a tool and get it underneath the rig or do other ancillary picks. Then there's crowd. And crowd on these rigs, and I'm pretty sure the lead bears are similar, is from this winch here, and it pushes and pulls on this drill rotary bracket that from Bauer is called a KDK. And of course, we can have different tools out there, so there's going to be different forces involved with different amounts of tools we put on there. The previous calc you did didn't have any tools in it. No, it did. It actually did have the weight of the tools in the base weight of the base machine for at least the Kelly system. An important thing to note in your owner's manual, when you start digging deeper, is that when Bauer calculates things, they calculate according to a European norm called 791. That's now replaced with a newer one. But in either case, they do the calculations like a triangle or a trapezoid. And this is the new version. It shows exactly the same formulas. So when you get a number from the catalog, at least from Bauer, I haven't dug into Liebherr's yet, but I'm pretty sure they're going to do the same because this is what their norm tells them how to provide the information. You get the triangular diagram. But for doing geotechnical calcs, we want the rectangular one. Plus, we might use different tools and different counterweight setups on the rig in the future. So, to really get the meat of the data, you got to go beyond the brochure to the owner's manual for that rig. And so in the owner's manual, it gave me that clause above, and then it gives me these diagrams here. And this is for the main rope case. So load on that main rope that supports the Kelly. And it says that I can put 355 kilonewtons on there, and I'm going to get a pressure working in the vertical situation of 430 kPa. That's 9 KSF. Whoa, that's a whole lot different than the 3 we had. And if I want to change the angle of the mast, like boom it down to make a bigger pick on that main line, I can get even 550 kPa, kilopascals, and that's 11.5 KSF. And this deals with the rig being sideways over here. You get the same number. And they have another case for the auxiliary rope and another case for the crowd rope. So now we're getting much bigger pressures, but they are the peak pressure, like at the toe of a retaining wall. And that's not what we want to use to design. If you're good friends with Bauer, you can get them to do a calculation for the particular case you're after. And this ends up being a replication of what's in the final manual that we got. And it shows that same 11 KSF. It also showed that it was done using that EN 791, so we know for sure it's a triangular distribution or trapezoid. If you're really good friends with Bauer, then, and this is from Malcolm's slide, then you can get them to do these diagrams. These are called butterfly diagrams, and for many years, Liebherr actually has this diagram in the cab for the operator. But still calculating a peak corner pressure. So this shows that as I rotate the rig around, I get here to about 30 degrees off the tracks, and that's my max pressure. Boy, we saw a lot of rigs with that type of orientation, didn't we? So this is really good information to know. The other thing that's amazing is you get around here to 90 degrees, and your pressure on the ground's way down. Now that's shocking to most drill operators. They realize that the tracks are longer in that direction than they are wide, and they think it's more stable in that direction. And it is if you're sitting on concrete. But if you're sitting on soil, it's better for the soil to operate that rig at 90 degrees. You can learn it from these graphs from Bauer. You can also learn that same lesson in the Federation of Piling Specialists spreadsheet. So we still got this dilemma. We got this peak number from Bauer, or Liebherr, or whoever, and we got to convert it to the equivalent rectangle. The challenge is we don't often have this minimum pressure that corresponds with that same maximum. And we might want to do something different with the tools, and we don't have time for them to get back to us. So we'll run the Federation of Piling Specialists spreadsheet to come up with the answers. Whoops. So now comes the real risk. I'm going to open Excel and an Adobe at the same time. So now I told you why you got to get involved with the why someone needs to look at this Federation of Piling Specialists spreadsheet. And you got from the owner's manual, you can get more detailed information further down in the pages I showed you already, with each component and its center of gravity. And boy, this actually looked a little better on my screen. So here, for the Bauer manual, center of gravity, a positive X means it's towards the mast from the center pin, a negative X means it's away. So you can break down the different components. And then you can take all those weights and eccentricities and bring them over here and enter them into this spreadsheet. And then if you want, you can change the drill tooling, because that might be the purpose of doing this. But for right now, I am completely trying to replicate the Bauer numbers that they gave me. So I'm going to keep the same drilling system here as there. In the process of doing this, you got to learn the drill manufacturer's terminology. So that rotary head for Bauer is called a KDK, not natural thing that comes to your mind. And you got to learn that you have a casing adapter and there's brake mechanisms, and learn the words that they use. But that's not all that happens. We're going to now apply forces to that drill rig through those winches. And so it's important to get these forces that you can apply, and those were the same numbers that were in the Bauer tables that I showed before, but I can also get them from the owner's manual. Down here, I can get 355 on the kilonewtons on the main winch, 140 kilonewtons on the auxiliary. And then this is a little bit of a dilemma. It shows me in my owner's manual that I can only get 200 on the crowd winch, but they did the calculations up above with 400 on the crowd winch. So I'll just keep the 400. I haven't talked to Bauer about why there's that discrepancy. And in the end, I'll show you why it doesn't matter much to me. And the tracks we input down here, the tracks are centered, they're symmetric, which makes it's good, makes it simpler. It doesn't matter which way you're operating a rig. That's not true with all rigs. Okay, so we got our stuff pulled over. Oh, wait, the other information we need to put in is the track width and length. We could get that from either manual, either the brochure or the owner's manual, but the center distance between the tracks, so that's from one track to the other, we had to get out of that PDF document that I had open. That was not in the brochure. And of course, how wide that is affects all these calculations. You got to define the geometry of your footing. So you input all that stuff, and then the calculations, there's a calculation for standing, there's a calculation for traveling, which I don't see as being different than standing. There's a calculation for handling, so that's the auxiliary line, penetrating, extracting, and so it's taking all those numbers over here and then running them through. It gives you both the front and the back of each track, and then gives you the equivalent rectangle bearing stress. For all those cases, you can even define another case if you want. And then that puts it all in a summary that looks like this. Well, that summary was a little quirky for me. I wanted a little condensed. So now, from here to the right is my spreadsheet, the additions to the spreadsheet that I did. So I did a different summary, and yeah, it's maybe not as pretty. But I also added in where I could where I linked over the peak pressure at the corner of a track and what the manufacturer said, and look at the ratio between the two. And for handling, we're within 14%. Little disappointing, but that's what I got. And for extracting, we're within 25%. Even more disappointing, but it's something. The other thing that comes out of it is we see that the ratio, and I'm coming up with lower numbers. or the FPS spreadsheet's coming up with lower numbers. From the FPS spreadsheet, we can determine our peak pressure compared to the equivalent rectangle, and for the most part, it's right around the 75%, which is nice, but I'm not sure it always occurs. It occurred for this rig. I think the other rig I looked at was similar. But so now we can go on and decide, well, now I got to go back a step. The one inconsistency I have is I can't get this penetrating number to tie. So right now it's off by more percentage. And I set it up so that I could play with what percentage of the crowd force I wanted to use. And I could change the number here. Shoot, this is where I wish I had a calculator. If I put a 100 in there right now, it won't solve it. So something's going different between the calculations, especially for penetrating. The spreadsheet says it can't even have that much force, and the Bauer numbers. And I bring this up in case any of you are working with this and end up with the same inconsistencies. Now, those pictures come into play, because I told you we didn't find a single rig that went backwards from penetrating. It would take a pretty extreme event for the driller. I think you'd have to have a driller have a heart attack, and I would think penetrating's pushing forward on the joystick. I haven't run a rig. I work in union environments. But I would think, he'd have to have a heart attack and fall forward and just keep pushing forward and basically jack himself off the drill tooling. We didn't see any pictures that happened like that. So for the most part, I'd say never let the penetrating case govern. Put in whatever number. What matters is walking and extracting. So then there's two different load cases. All these ones where the driller can't do much, standing, traveling, and handling, are called load case 1. And they require a larger factor of safety, whether you have the gravel or don't have the gravel. The other load cases, case 2, are penetrating and extracting, and the reason that, and they have a lower factor of safety, and the reason is that as long as your driller's conscious, he can make corrective action. He can feel, there's instruments on the rig that tell you the inclination of the mast and stuff like that. He can make corrections to stop that from happening. Okay, so let's go back to the presentation. So here's a bar chart of all these analysis that we've done. We had the simple calc where we got 3 KSF right here. We got a little bit higher peak than Bauer here. But then once you start into the penetrating and this penetrating, the reason the peak is lower than ours is I forced it to not govern ours. And extracting, Bauer gets a little bit more. I'm going to cover the simple method later. Yep.
When you use the term stand, is that the same type of work as moving? Because all of a sudden it shows the rig was moving.
I'm not sure they were all moving. Most of them, the videos certainly were. Right now, I don't see the difference in the calculations whether it's standing or traveling. The Federation of Piloting Specialists spreadsheet, I don't see it handling anything different. And really, there's a kinematic effect of, you got this weight that you're stopping when you're tracking or starting when you're tracking. That's not in here right now, from what I can tell. I always get the same answer, standing versus traveling. I suppose you could put some other weight in while you're traveling. I don't know. Okay, here's a simple method. If I don't have anything on a rig, and so the stuff I'm showing you was manuals from 2013. Rigs older than 2013, maybe 2010. The stuff in the manual is real obscure. And we have a bunch of micropile rigs that we bought when I started work there. And there's very little in there except the total weight of the rig. So if you have nothing, you know the weight of the rig, and you know how much force you can pull with. This pulling force is like an external force on the rig, right? So it's an extraction force. And you don't really need to know the centers of gravity if you assume that it's perfectly balanced. You're about to tip the thing over with that max extraction force, which is conservative. There are, with cranes, the rule is it can only be 75% of the load that'll let it tip over. I'm not sure what the rules are for drills. But so now you can say all this force just goes on one track. If you got nothing else, that's a way of coming up with a number. And you can also check what happens if I'm holding my tools and use the other line, which is this auxiliary line, then your formula is this. So in an absolute worst case, that's the upper bound. So if we graph all this stuff versus slewing angle, I didn't describe slewing angle. My tracks are sitting this way. Slewing angle is I'm rotating the house of the rig around this way. You can see that the penetrating one is still set up as, it's close to governing. It's got a lower factor of safety, and it's kind of wacky. An extracting one, I'm sorry, handling is higher than extracting. When you're extracting in the Federation of Piling Specialists spreadsheet, the weight of the tools, which are pretty significant, are on that main line. It's part of the extraction force, so you've already accounted for the tools. You don't want to double count them. So you can see, kind of like that butterfly diagram for that one particular Malcolm rig, that if you're at 90 degrees, you minimize the stress you're putting on the ground. But it's even better than that. No, that's not true. You're minimizing the stress you're putting on the ground. And if you're trying to see, am I in the peak versus rectangle case, if I take those same numbers and graph them just as a percentage of peak versus rectangle the whole way around, you can see at 90 degrees, we're at a rectangle. But for a lot of the other numbers, we're down here near the triangle type condition. And you would think that this is a problem, the 90 degrees, but if you really look at it as the rectangle from 90 degrees divided by the overall peak, again, you see that 90 degrees is the best place for the ground, the best place to run this drill. Okay, so what did we learn from this spreadsheet? There's lots of details to track. That crowd case can really blow up, but I don't think somehow something's not getting handled right between us and Bauer, between the Federation of Piling Specialists and Bauer. The equipment manufacturers are giving you the peak pressure, and as long as it's triangular, it's 75% of the peak, and it kind of turns out that most of the time when they're in the max operating condition, it's pretty close to triangular over the full track length. Okay, now we get into working on the geotech side. We might all get involved with doing those detailed calculations and tracking of things and understanding the forces that are applied. You really need to understand how the forces get applied for something to be worthwhile. So there's a different document. BRE is the Building Research Establishment in the UK, and they've used this model for putting a granular platform over a subgrade. And so here's a blow up of it, and the idea is you have a bearing capacity down here, and this gravel is going to reduce that by friction on the sides and also on the ends. One of the things that, one of the first versions of this spreadsheet we ever did, sorry, my phone's ringing in my ear, spam. One of the first versions of this spreadsheet we ever did, we said KP. Okay, let's use Rankine KP. And we were just getting these ridiculous gravel thicknesses. So this particular diagram is not your typical KP. In fact, the formula that's used for KP in a Soliton spreadsheet is apparently called a Brinch-Hansen KP that I can't even find. But the idea is to match, you want to basically replicate their model. So if I come back here to my spreadsheet, if that's their design method, let's make sure that we're coming up to the same calculation. So these orange squares are what happens with a Soliton-Spassky formulation for KP tan delta. At one point I was trying to do a quadratic fit, and in the end I said, you know what, I'm just going to go with their equation. So it's close. Sometimes, you know, you get up here to some pretty high friction angles. This is gravel, so we can get some pretty high friction angles out of it. Then there's a little bit of divergence. 50 degrees, it's more divergent than their line. So the other lesson is it's important to keep going with the model. Once this is the system they're using, keep going with their system to calculate things. Let's just cover that while we're here. So that's the basic model. The bearing stress underneath is either CNC or 1/2 gamma n sub, I can't remember which one that is. It's not n sub q, it's n sub gamma. Those are all following the Meyerhof formulas. Maybe I should go back to the PowerPoint a second. What I have noticed recently is that their methodology doesn't take the benefit of this surcharge pressure, the thickness of the gravel on this bearing capacity down here. There's a little bit of conservatism there. KP tan delta may feel pretty high, but there's conservatism in the number they're using underneath here. Just something that's in there, but it's the system. So I set this up, so I got 5 different cases I can run, and I can put on the numbers here and just look at the answer in gravel thickness right here and compare things. And it turns out that if you use 2,000 PSF for cohesion, you come down to the minimum 1 foot recommendation that's in the Federation of Piling Specialists and BRE methods. That's pretty decent ground. You may wonder why you're putting piles in ground that has that type of cohesion. And the challenge is if you have just friction, then you end up with pretty substantial gravel thicknesses. And it's made a little bit worse by the fact that that gravel isn't considered a surcharge on the resistance from below. But that's the system that's been used. So use the Federation of Piling Specialist spreadsheet, you get some numbers that are lower than the triangulars and have trouble tying to Bauer. But then you continue on with the model that they use. It might have other conservatisms in it that kind of counterbalance each other, and their system's working. I know of no rig turnovers on jobs in the UK that had work platform design processes. But certainly a rig sitting, and bearing capacity on sand without embedment is really poor. And so it's a challenge to make that work. You almost always end up with gravel if you use a purely frictional model for the subgrade, unless you use 45 degrees for the subgrade, and probably you don't need piles if your subgrade's 45 degrees unless it's really soft down below. So there's some challenges there. And that gets us to these slides. I don't have the details of these rigs, but I can tell you that one's sitting on this one. Where's my arrow? This one's sitting on sand. He's working at he's working off the corner of the tracks, so it should be pretty high under the toe here. That one I think would be hard to calculate. Here's another one. And now he's getting right down near the water. And here, these ones are submerged, and they're still working without some other system underneath. And maybe they're not BG39s, and maybe they're not applying 11 KSF, but I'm telling you that a rig sitting on that type of ground is going to be hard to calculate. So what makes this work? Well, we all know we can drive cars on Daytona Beach. And that is something that's missing. So that surface tension that lets us drive cars on Daytona Beach, and it exists in this sand here, and probably this sand here, is what makes things work. So there are other phenomenons that are helping our rig be stable that aren't in the methodology. And we need to appreciate that's out there rather than just using a V equals 30 degree subgrade for the calculations. So I had a whole lot of rig geometry stuff and not a whole lot on this bearing capacity stuff. Certainly part of those formulations is the length of the equivalent rectangle, so it looks at the various correction factors for the length to width ratios. But the bearing capacity is kind of a simple formulation, and it's using Meyerhoff. The next topic that is currently being dealt with within the industry, and really it's more the Europeans advancing it, is what do we do to test the site so that our operators, so that we're not just putting it all on the operators. Right now, we show the operators a video, and what are they supposed to do? They're supposed to get scared. I don't know what, we aren't giving them any answers. So the idea is to look at proof rolling. If you can drive a loaded concrete truck over the subgrade, that's a pretty good sign. And there's lots of other things being investigated. And so this is where what's coming in the future is how do we then confirm that the site's okay. That's all I have. I'll tell you one more story that then ties into who should be responsible. And I didn't have any pictures in my presentation just because I didn't dig hard enough to find it. It's not in my regular directories. We had a rig, a modest size, a BG-18, doing a seek and pile job, and I actually did calculations for that job. And there was an alluvial clay that wasn't saturated at the surface, and from blow counts and some pocket penetrometer numbers, I thought, this is okay, we'll just put the 1 foot of gravel. One of the few jobs we actually did the calculations for. That's a whole nother story. But, and on that particular job, one of the few rigs we've had get in such precarious situation, the rig went over. We had actually done the calculations and the rig went over. But he went over in a hole that the GC had dug and doing the site preparation work to disconnect a utility or something. So we can't just put it all on the drilling contractor because the GC controls what really goes on the site to stuff that we can't really investigate. Even if we come out there and proof roll, we might not find it. And so everybody's got to be involved and educated and concerned about this because if a rig goes over, it's a bad day for everybody. Okay.
So in your model there, I didn't see
Hey, can I have my PDF back?
So in your model, I didn't see a factor in there for the geogrid and how that
I'm
affects.
sorry. Yep. It gets converted into a tension. I guess you're right. I do not show that particular. It's in my it's in the spreadsheet, but you're right. I don't have it in here in terms of the model.
So do you have an input parameter that you can put in different types of geogrid?
Yes. So you input the geogrid, and it takes the strength of that geogrid And I don't really know, other than it's in their formulations. I have not studied how mathematically that tension in the geogrid gets converted into punching shear resistance. But it's in their formulas that go along with this diagram. This diagram here. And it's in the spreadsheet. And so this is a plug number of 30 kilonewtons per meter. 2,000 pounds per foot is a tension strength of the geotextile.
What is the geotextile? Is that geogrid or is that something else?
Well, I'm just running numbers. I haven't actually used one in production. We just did gravel in production.
Would the gravel thickness be less than geotextile?
Exactly.
I mean, how long is that?
Oh, boy.
Seems counterintuitive.
It is less. So shoot. I made some corrections to this spreadsheet in the last week, and now I got some other corrections. There is no doubt the answer is less with the geogrid. These pages here were developed by some combination of Solitanch and one of our engineers, and then we found this KP tan delta issue. Solitanch has a whole nother spreadsheet now, and I thought that I had all these things calibrated to the new spreadsheet and corrected all the things, and now I can't explain why the geogrid hurts. It doesn't, so it must be pulling over the wrong numbers, because here, I'm just converting a number wrong. There it shows it, so it's just this, right there, it's a conversion.
I'm very interested in the spreadsheet once you fix it.
Well, so I will. Thank you for pointing out the error. I really thought I had this tied in and back-checked with the Soliton spreadsheet that I can also share. The reason it's still using this one is this one can actually let you put a CFE material in, the Soliton spreadsheet, because the manual is set up for either cohesion or friction. That's how the Soliton spreadsheet was set up. If you want to do a CFE material, maybe make some estimate of the surface tension in the water, you could put that in as a cohesion. So yeah, thank you for pointing it out, and I'll get it fixed.
Well, I have a little less embarrassing question. So those of us that work in environments where we have good ground all the time and have rarely had to do this, tell us in the practice where you're working in bad conditions, like you showed where these rigs overturn, what is the typical good practice? Is 1 or 2 feet of gravel over a grid or a fabric now the norm? What's the normal good practice you see in the field?
So the Federation of Piling Specialists recommends 1 foot minimum, or designing with the higher factor of safety. With this particular rig, you have to have ground that's nearly 40 degrees friction angle just to deal with these bearing stresses. I mean, you're looking for ultimate bearing stresses of 11 KSF. Those are big numbers. And then I did this row here as a simple, what type of blow count do you need? There's an old rule of thumb I learned in my first job, a ton for 10. 1 TSF per N value of 10. And it comes from Peck Hansen and Thornburn graph of things. So, you know, it's just a simple, do I blow counts of 19? Do I stand a chance? So really, if you have that type of ground, blow counts in 19, then this rig should stand on it. But they'd have a different factor of safety for no gravel. If you can live with that factor of safety and with those type of soil parameters, it only took 2.3 KSF cohesion. And this is a big rig. So for the most part, it's 1 foot min.
He's already got your name.
Well, for the British standard, they heavily relied on the plate load test, 300 millimeter load test. But regarding when we have a heavy drill rig, like a power drill rig, 1 meter wide track and 5.3 meter equivalent length, So what's your opinions about this representative get a meaningful input to evaluate the working platform use a plate load test?
I have never been impressed with a plate load test for any purpose. I'm sorry, it's just too small and influences too little ground. For viro compaction, stone column jobs, I think it's just it doesn't prove anything. I think it's completely wrong. We had a drill, not quite as big as this one, on a job where we pulled out the number from the catalog about the bearing stress, and in order to proof roll the site, the GC had to load up Euclids and calculate the pressure, not including the tracks in the Euclids, not including the grooves in the Euclid tires. He had to look at like pure contact stress to prove it that way. That did end up being successful, except when he disagreed about the test area. He agreed he should provide a work platform for the production area, but not for where the test piles were going in. That's the type of games we get into with GCs. Yep.
All right, so I can only speak to my experience in Southern California, but who is generally responsible for preparing the work pad that the equipment operates on? Because we're asked on every project to design the crane and the outrigger and the support, but never for the drilling equipment.
Well, right now we don't have an official who's responsible. We just want to have a discussion among the team. And that US document that I showed basically says, here's the type of things that the project team should discuss and figure out who's taking care of this, and at least all communicate and realize that this is an important topic.
Yeah, I would agree. I have a lot of pictures of equipment laying down sideways, but never a crane. So.
Crane mats are remarkable. You can add them to this calculation. You know, just make the track 4 foot by whatever, 20 foot, let's say, if you're going to run along the crane mats. And if you're going to run a perpendicular to them, you can make it the full like 20 by 20 underneath the rig. And in our practice, just because of the nature of the projects we've been doing, we've been putting these big rigs on crane mats. But it's because of the product. We're building seek-and pow walls. So you can line the tracks along the seek-and pow wall. Or you're doing a shaft, and so they're sitting in the middle of a shaft doing the work. So it's putting down crane mats isn't that big a deal. We did move them around, not full-size wooden crane mats. We moved plastic crane mats around underneath the BG39 and the BG30 on a soil mixing job. So the mats really work.
Other questions?
Yeah, one more. How about treated soil, like cement treated soil?
I met the guys back there yesterday and said, hey, I don't have anything in my talk about this. I tried to mention there are guidance documents out there in the European documents that talk about how to handle that. It's like another publication of this BRE thing, or a different one. I haven't studied them yet. As part of our committee, Peter Faust from Malcolm sent out a test problem for us from somewhere out here. And on that particular site, there had been lime or cement treatment of some of the ground, of a layer of the ground, and then granular fill put on top of it. And so that became a challenge. How do we deal with these two different systems in doing the calculations? And then in the end, Peter told us what worked, but I don't know that anybody's ever figured out the best analytical method when they're combined. But there are methods out there for lime-treated material or cement. Something with cementation.
Yeah, one more question. So you mentioned that you have a simplified method to compute the pressures. Is that different than the FPS? You had it in one of your spreadsheets.
Yeah, because it's conservative. It says that when I turn my rig 90 degrees and put the full extraction force, I'm about to tip over the rig. All the weight of the rig and the extraction force are going on one track. And the only reason to do it is when you don't have enough information or enough time to go through the detailed calculations. But really, my purpose in showing it is for if you got a rig that doesn't have a detailed manual like that, that's, you know, let's say 2005 or older, you got to do something. At least it's a way of doing it.
We had started a little late, so we're going to let questions just go on a couple more minutes if there are any others. All right, I'll make my way back up to the front.
I got one other comment. I think if anybody uses any of the images or videos that you can find as negative marketing against another contractor, you're basically asking for you to be the next one to lose a rig. That is bad karma. So I don't want to hear about any negative marketing.
So Tom, thank you. We have a small appreciation gift. If we could give an appreciation round of applause to Tom, please.
This is a post-presentation supplement to show two things. The first is about the error in the spreadsheet pointed out by one of the questions, and the second is new information I've learned from Bauer. So here's the spreadsheet that was sent out to the California attendees afterwards, where this column now has higher numbers for the gravel than the gravel with geotextile. And it was purely a poor reference. That cell that was referenced right there, it was just not the critical one for the gravel case. The second topic deals with the Bauer manual and comparisons I made to the Bauer manual. In the crowd, and what I learned from the Bauer representative is that the crowd presented in the Bauer manual is pulling with the crowd winch, not pushing. And so for the pushing case, he says that the force is electronically reduced and has a lower value than the pull force. And this shows up in new manuals where it gives a very different number for pulling with the crowd winch versus pushing with the crowd winch. There's two other factors that cause the difference between Bauer and the Federation of Piling Specialists. And this isn't just Bauer, this would probably be anyone doing the calculations for the rig stability under this Euro norm. And that's that they have the consideration of accelerations as you lift the load, accelerations as you travel, as you slew, and for adjustment of the leader. The other things that European rig manufacturers would have in their combination of loads is consideration of wind loads. And so here's the pressure that's supposed to be used in normal in-service cases. So does that mean that there's problems with the Federation of Piling Specialist spreadsheet? I suggest not, because the wind and acceleration effects are short-term loads. Most soils perform better under short-term loads that are not cyclic. And if this was done in load combinations or with consideration of different factors of safety for the frequency of an event, these short-term loads would have a lower factor on them and would likely not govern. And the final point is that the Federation of Piling Specialists spreadsheet has been used successfully in the UK, along with the BRE method of calculating the gravel thickness. Thank you and have a great day.